welcome to the last video for Calc 2. All we have is one more example and then one short little topic to discuss. It's not quite everything I wanted to go over this semester. I cut chapter 9 just a tiny bit short, but I wanted to try to give all of the highlights for those of you continuing on to Calc 3 and then continuing your mathematical career. So without further ado, I wanted to do an example where we find a Taylor series for a function. So there's some specific center that is not 0, and I'll go through that relatively quickly because the process is almost exactly the same as what we're used to. The formula for our Taylor series, if we remember, looks like this. A function is the series from 0 to infinity, where I have the n derivatives here of our function evaluated at c, divided by n factorial times x minus c to the power n. Okay, and again, I want to write this out in its kind of expanded form. I don't have a lot of room here, so I'll just do a couple terms. The original function at c plus the derivative at c times x minus c to the first, and then the second derivative at c divided by 2 factorial times x minus c squared, so on and so forth. And the example I want to do here is with cosine of x. I'm going to find a Taylor series representation for cosine of x where the center is pi. All right, so this will be the only example that I do. Again, it's not really any different than finding a Maclaurin series. It's just that now I'm plugging in something other than 0. I go through the same type process. For n is 1, or I'm sorry, for n is 0, getting ahead of myself, I take the original function, which is cosine, and I evaluate that at the center, pi. Cosine of pi is a minus 1. For n is 1, I take the first derivative, that's minus sine of x, evaluate that at pi. Sine of pi is 0. Okay? And keep going. When n is 2, I take the second derivative. Derivative of minus sine is minus cosine, evaluated at pi. Cosine at pi is a minus 1 times an extra negative is a 1. When n is 3, third derivative is sine. Plug in pi, I get another 0. Fourth derivative is cosine, evaluated at pi, and I'm back to where I started. That's a minus 1, just one more. Plug in pi to the fifth derivative, and I get another 0. Okay. So what we notice here, when we were dealing with the Taylor series or Maclaurin series for sine of x, it was all the odd terms that showed up and all the even terms that disappeared. For cosine here, we're in the opposite scenario. All of the even terms are going to remain and all of the odd terms are going to disappear. So what I do is I write what I found here, these derivatives evaluated at c in for their respective place in the Taylor series. Okay, so my function then, cosine, should be minus 1 for the first term, that's the function evaluated at c, plus 0 is the derivative evaluated at c, times x minus c, which is pi, plus the second derivative is evaluated at pi, is 1, divided by 2 factorial x minus pi squared, plus another 0 for when n is 3, x minus pi to the third, plus the fourth guy there is a minus 1. And again, that comes from this minus 1 here. And I have then divided by 4 factorial x minus pi to the fourth, plus so on and so forth. I don't have room for that fifth term there, but I think you get the idea. That would just be 0 anyway. I'm going to simplify this, right? I'm going to take away all the terms that are going to be 0, and I'm going to leave then all these even terms. I'll even include the sixth, what would have been the sixth term when n is 6. I get a minus 1, plus then the second derivative piece comes. I have x minus pi squared there. The third piece is from when n is 4. When n was 4, I'm going to change it. I've got minus 1 over 4 factorial x minus pi to the fourth. And then what would I get next would be, I alternate again. I'll get a 1 on top, divided by 6 factorial, x minus pi to the 6th, so on and so forth. So when I condense this, again, what I'm going to try to do is, instead of, I'm still going to start n at 0, but instead of, just dealing with these terms that disappear, what I'm going to do is ignore those completely and just obtain, when n is 0, a minus 1. When n is 1, this guy here. When n is 2, I get all of this. When n is 3, that's when n was previously 6. So what I want is all the even terms. And if you remember, the way to handle that is with a 2n. Remember, odds were 2n plus or minus 1. Evens are just 2n. So cosine of x then is written summation from 0 to infinity. I have an alternating sign, right? So the first term I get when n is 0 has to be negative. That's contrary to what we had before with sine of x, right? So the first term has to be a minus, so I have a negative 1 to the power. If I were to try n, when n is 0, that's negative 1 to the 0, that's a positive 1. So that does not work here. What I need is negative 1 to, say, the n plus 1, or n minus 1. N plus 1 is usually what we do. So when n is 0, I have negative 1 to the 0 plus 1. Negative 1 to the first, that's a minus 1. So I get the correct expression then when n is 0. In the denominator, I'm going to get even factorials, right? When n is 0, there's a 0 factorial down there. There's a 1 that shows up. When I start to see something is with the next term. When n is 1, I need a 2 factorial in the denominator, a 2 factorial. And the only way I'm going to do that is if I have 2n factorial in the denominator. When n is 2, I should see 4 factorial, and I do when n is 2. When n is 3, I should see a 6 factorial. 2 times 3 is 6, then factorial. The power of x minus pi should be the same, right? There's an x minus pi in every term except for the first. Well, if I have x minus pi to the n, when n is 0, that's just 1. And the negative alternating part will give me what I want there. But the next one would have to be when n is 1, I would need an exponent of 2. And the only way I can do that is if the power is 2n. Okay. There's my series for cosine of x, my Taylor series for cosine of x, around the center of pi. Okay. In fact, this guy is what I want. And we're able to show with the ratio test that this guy also, I say also because the previous examples converge for all x, this guy also converges for all x. So there's just one example of finding a Taylor series. It's very similar to Maclaurin series, just now the center would be defined. And in a specific example, on a quiz or test or in the practice or in the homework, you would have a center that's specified. Like here I told you, find the power series for cosine of x when the center is pi. That's always going to be a given. Okay, now, this is a Taylor series. The next thing that we're going to talk about is a Taylor polynomial, and that's bringing in section 9.7 here, Taylor or Maclaurin polynomials. And those are slightly different things. It's basically just a Taylor series, but I'm going to stop somewhere. I'm going to say, I only want so many terms. And what we're going to do there is then use those as approximations. Okay, so this is now section 9.7. Going into here, not necessarily done with 9.10. I group them on purpose, right? Because they're so related. I do the whole series first, and I say, well, what happens if we only do so many terms? Well, what we get here, say we want to approximate. We want to approximate a function f of x. We can do that by using the Taylor or Maclaurin polynomial. Instead of the series, we use the polynomial rather than the Taylor or Maclaurin series. Now, an important note here is the following. I'm gonna write this out, and we use this notation P subscript n. That n is going to determine basically the degree, or kind of the power, basically, of the polynomial that we're going to use, basically the number of terms, or similar to the number of terms. Not exactly. And again, that's just some nth degree polynomial. So I'm going to write my Taylor series, but instead of making it infinite, it's just going to stop at, say, the nth term. And again, our important note is that the polynomial has a finite number of terms, where the series has an infinite number of terms. So they are slightly different things. The polynomial is used to approximate. You'll see I've got my squiggle, my squiggly equal sign. It's my approximate sign, right? This is not exactly the same as the function. It's close, or it can be close, just depends. Depends on the function, depends on the center, and depends on which x's I'm looking at, okay? So I'll do an example here, but what I want to say, of course, if the center is 0, P sub n is called it's called the nth degree Maclaurin polynomial, right? So it's just a specific case when the center is 0. That nth degree is basically what's going to determine how many pieces parts we have, the degree of the polynomial. So I want to do an example here. I want to find the 4th degree Taylor polynomial. I'll go right to Taylor here. Maclaurin would just be with a center of 0, of natural log of x centered at c equals 1. Okay? And then I'm going to use that 4th degree polynomial, p sub 4, to approximate the natural log of 1.1. Okay? I'm going to try to speed through this process. It's really basically the same as finding the Taylor series. We just don't have to then generalize the formula. We get to stop at when n is 4. Okay? So I'm going to go through. I'm going to say this is the polynomial that I want. My function is approximately the same as this 4th degree polynomial. And then I write out the first 5 terms, really, right? When n is 4, I have 5 terms. If I start at 0, first 5 terms of my Taylor series. F of c plus f prime of c. Ooh, I actually forgot. There should be an x minus c here. Forgive me. F double prime of c over 2 factorial, x minus c squared, plus f triple prime of c divided by 3 factorial, x minus c cubed. And then the 4th and final piece there is the 5th term, right? So I've got 5 terms here. 1, 2, 3, 4, 5 of the 4th degree Taylor polynomial. And I know it's 4th degree because x minus c to the 4th has x to the 4th as a power. And that's the highest power of this polynomial. Excuse me. So I go through the process I did before. I let n be 0. I find the function evaluated at the center that I'm talking about. That's 1 here. So I take natural log of x, I evaluate it at 1. Natural log of 1 is 0. Cool. Easy enough. When n is 1, I'm looking at the first derivative. Derivative of natural log of x is 1 over x. Evaluated at 1 is a 1. Okay? Keep going. I need 4 total, or I need when n is 4, so I need 5 total. So I need 3 more. When n is 2, second derivative of 1 over x, or x to the minus 1, is minus 1 over x squared. Okay? Plug in 1, that's a minus 1. Third derivative is going to give me a 2 over x cubed, and plug in 1, that's a 2. Fourth derivative, this is the last thing I need here, is going to be a minus 3 times 2 over x to the 4th. I'm out of room. Plug in 1. That's a minus 3 times 2. Okay. Now, all of these are going to show up here in my series as the coefficients. Okay. And then I'll simplify. So what I've got is that natural log of x is approximately the same as this 4th degree polynomial. And this 4th degree polynomial should be 0 plus 1, and again, all of these are coming from right here. 0, 1 x minus 1, that's my center, to the first, plus minus 1, when n is 2, again, that's minus 1, over 2 factorial x minus c squared, x minus 1 squared, plus, when n was 3, I got a 2 over 3 factorial x minus 1 cubed, and then a minus 3 times 2 over 4 factorial x minus 1 to the fourth. Okay, and again, just a little bit to simplify here, I see this 0 is going to disappear. I can also do some cancellations here. If you remember, say 3 factorial is like 3 times 2 times 1. So I'm able to cancel a 2 there. And a similar thing, 4 factorial is 4 times 3 times 2 times 1. And I'm able to cancel the numerator. And that's going to happen basically in every term here. So what I've got, shorthand or simplified, is P4 is 1 times x minus 1. It's just x minus 1. Minus 1 half, right? 2 factorial is 2. X minus 1 squared. Plus 2 over 3 factorial is a third, x minus 1 cubed, minus 3 times 2 over 4 factorial is just a fourth, x minus 1 to the fourth. And that's approximately natural log of x. Okay, so right there, that's my fourth degree Taylor polynomial. That's basically my answer here, my fourth degree Taylor polynomial. All it is a truncated version of your Taylor series. You're stopping at a specified number of terms or a specified degree. And what we can do is we can use that to then approximate our natural log of 1.1. All that is here, since 1.1 is close to our center of 1, in fact, it's just off. What's the difference between 1 and 1.1? That's just 0.1. So really, I should see a difference of kind of like 0.1 in every one of these x minus 1s. So I'm taking every x and I'm plugging in then 1.1. So for all of these x's, I'm going to plug in a 1.1. And I'll do the estimate for you here. It should be 0.0953. Versus, what is the actual? What's the actual? What is exactly natural log of 1.1? If you plug it into your calculator, you get something that looks like this. 1017 ... That's not bad. Not bad at all. The approximation is good up to 4 decimal places, which is awesome. That's awesome. We're able to approximate our function with pretty good accuracy just using a polynomial. Yes, of course, we have a calculator. We can just type in natural log of 1.1. Sure. Yes. Where this is nice. So just a quick recap. I took my Taylor series and I said, let's look at the first 5 terms. Let's look at the polynomial I get by going out 5 terms with a center of 1 for natural log of x. Okay, so I took my derivatives. I calculated that polynomial. That's P4. And then I used that to approximate what natural log of 1.1 would be. This wouldn't be so good if I would to approximate like natural log of 12, right? That's very far away from my center. So the further you are away from your center, the more bad the approximation gets, right? So I wouldn't want to approximate natural log of 12 by using a Taylor polynomial centered at 1. That doesn't make any sense. I would center it at 12 or something else. Center it at 11. Something I know about. So in general, the Taylor approximation is good near your center, especially in a case where I look. I don't necessarily want to find the 12th degree polynomial or the 15th degree polynomial. This is a nice kind of approximation if we can do it quickly. And that's really the case where we're looking where n is 1. These approximations are especially nice or especially useful when n is 1 or P1, where we have f of x plus f prime of x times x minus c. Okay, you've actually seen this before. It just wasn't called a Taylor polynomial or a Taylor approximation. Why is it nice when n is 1? We do indeed get better accuracy for larger n. Okay, you can try that out if you like. But when n is 1, things are easy to calculate, right? I've got my function of x, and I've got my derivative. In fact, those shouldn't be x's, those should be c's. I apologize. Those should be c's. I've got my function evaluated at c, my derivative evaluated at c, and that's really all I had to calculate. This is going to give me an okay approximation from my function, and all I've had to do were to compute two terms. You've seen this before. This is actually just called the linearization. The linearization of f at x equals c. And the reason it's called linearization is because this expression is a linear function, right? The variable here, x, is to the first power. All I've got, spoiler, this is the equation of the tangent line. It's just the equation of the tangent line. And you've been calculating that for a long, long time now. And it's just the equation of the tangent line at x equals c. It's an easy thing to calculate. It gives me an approximation for my function near c, near kind of our center, and it all comes from Taylor series. It all comes from our Taylor approximation, our Taylor polynomial. It's super cool. It's easy to calculate, and it can provide a decent approximation for what we're looking for. Linearizations are used all over the place in your engineering, in your physics, in your chemistry. You're using linearizations of complicated formulas and equations and solutions to come up with a good guess for what you should be getting, for a good guess for what your answer is. You just don't necessarily see it all the time. The linearizations are already done for you. They've taken this really hard, complicated mathematical stuff and they've linearized it. Okay, they've turned it into a linear function that you can just plug things into. And those are most of the formulas you work with today. And that's it. That's all, folks. Thank you for a great semester and have a fantastic summer. Thank you all for hanging in there with this transition to online stuff. It was difficult. You know, it's been difficult for everybody, you, me, and everything. Good luck with your finals, including mine. As always, you know, if you have any questions or need any help, you know where to find me. Thanks for watching all of these if you did, and have a great summer.